Okay, today we're talking about logarithmic functions. All right, so before we begin, let's have us a brief review of some characteristics of functions. Okay. So again, all this can be found in section 2.7 as we see here. But a brief review. All right, so first of all, only one functions have inverses that are functions. So remember that little hierarchy of functions that I described to you, right? We had equations followed by functions, followed by one-to-one functions, and then only one-to-one functions have inverse functions. So a function f has an inverse function uh, if there's no horizontal line that intersects the graph of f at more than one point. We know that from the horizontal line test. Number two, if a function is one-to-one, its inverse function can be found by interchanging x and y in the function's equation, solve for y. That little four-step algorithm that we did to find the inverse function. Three, if f of a is equal to b, then we know that the inverse of f of x is f inverse b is equal to a. The domain is f and the range of f inverse is, the domain of f is the range of f inverse. The range of f is a domain of f inverse. So really quickly, let's touch on that one just for a moment, okay? So if we have f and then we have f inverse, okay? And let's do domain, range, domain, range. All right, so just if the domain of f is, we're just going to call it some alpha, and the range is some beta, well then the domain of f inverse is going to be that same beta, and the range is going to be the alpha, okay? So notice how they are exact opposites of one another, okay? Moving on to number 4, if we take the composite of f and its inverse, we should get x. And then 5, the graph of f inverse is the reflection of the graph of f about the line y is equal to x. Remember that we had, if we had some graph here, then the reflection is about this line right here, okay? And that is the line y is equal to x, right? And again, if you need more information, a little refresher, you can go back to section 2.7 and check it out. Alrighty, so talking about logarithmic functions, and we're gonna put this over here, and we're gonna put the other definition over here because I gotta write some stuff here. Okay. Not really. Well, I mean, yeah. I'm just gonna rewrite. I'm basically gonna rewrite what I'm snipping right now. Okay. And we'll put that in the middle so I can work on it. So the definition of a logarithmic function: if we have some x that is greater than 0, okay, it has to be greater than 0, and b which is greater than 0, with b not being equal to 1, then we have equivalent statements. Y is equal to the log, and we say base b, right? It's below the log. Base b, it's the base, is equivalent to b, again, that base of y is equal to x. The function f of x equal to log base b of x is a logarithmic function with base b. Now, let's turn our attention over here, and these two forms are more or less interchangeable, kind of, right? We can go from logarithmic form to exponential form, and from exponential form back to logarithmic form. All right, now this is how I like to showcase this. Okay, so let's start with. Now you just start with exponential first. So let's just go ahead and start with exponential. Okay, so we're gonna have a base b raised to, and again I'm color coordinating this, so pay attention. Okay, we have b raised to the y power is equal to some x. Okay, this is equivalent to saying y is equal to log base b of x. Okay, now all I did was rewrite what this says and what this says. All right, that's really all I did. I just rewrote it, but I color coordinated it so you know more or less what goes where. Okay, uh, this particular part of this of the section is really just a an exercise in, you know, rearranging. Honestly, you just rearrange exponential and logarithmic equations. So, without rambling too much, let's go ahead and look at example 1. Okay. So example 1 reads, write each equation in its equivalent exponential form. Okay, so as you can tell, they're in logarithmic form because we see the word log, and we want to write them in exponential form. So A, right, is a log base 5, so that means we're going to have a 5 as my exponent, and then the 2 on the other side, so it's 5 raised to 2 power, and that's going to be equal to some x. Okay, and that's it. All we're doing is rearranging from logarithmic to from logarithmic to exponential. Okay, so again, this is log base b of 64, so we're going to say, all right, well, the base is b. Okay, and then what's on the other side of the equal sign is a 3, so b cubed, and what is b cubed equal to? Well, it's equal to 64. And then c, we have a base of 3. What's on the other side over there of the equal sign? It's a y, and that is equal to some 7. Okay, and again, all I did was just follow along with this kind of, you know, I mean, I guess they are formulas. I feel like there's a better word, but for right now we're gonna stick with formulas, I guess. All right, so all I do is follow along with that. We went from logarithmic to exponential, right? I said base b, and I said what's on the other side of the equal sign, right? And that says equal to that x. So all I did was follow along to that. Okay, and we don't have to solve, so we will proceed. All right, we will solve, but we didn't have to there. All right, so now we're going to go from exponential to logarithmic. Okay, so in example 1, we went from logarithmic to exponential. Now we're going to go from exponential to logarithmic. So again, I'll be using the same idea that we did on the very first page, right? Kind of interchanging back and forth. So this is, we see the 12 is the base there, right? So we're going to say log of 12, okay? Log base 12 of what? Okay, well, it looks like of x, right? And that's going to equal to the other, I'm sorry, it's going to be equal to the exponent, which is a 2. Okay, and then b, we have a log, and then the base is b, so log base b of what? Of 8 is going to be equal to my exponent, which is 3. And then c, log base e of 9 is equal to e. No, sorry, is equal to y. Okay. Now it's I don't want to say it's necessarily hard to tell on this blackboard, but I have seen in classrooms that some students, like for instance here, might write it like this: log of e raised to, and it looks like raised to the 9th power. Okay. Now again, this is just, I wouldn't necessarily, well, it's just it's a common mistake, especially based on how maybe I write them. But the 9 is in line with the log. Only the e, or only the base is below the log. Okay. All right. So we're gonna have some basic logarithmic properties. They're pretty basic. Let me see if we have more. I'm sure we do. Oh, we don't. Oh, we do down here. Oh well. Okay, so let's go ahead and just go ahead and snip this and put it below it. Okay, so we have the basic logarithmic properties involving a 1. All right. So if we have some log base b, and then by the way, the number or constant or anything that's out here next to a log, we call that the argument. So log base b of b, right? We would say log base b of b. The of b is the argument. Log base b of b is equal to 1 because 1 is the exponent to which b must be raised to obtain b. And again, we see that as if we were to rewrite this logarithm in exponential form, we would say, okay, what's the base? What's b? What's on the other side? What's a 1? So b raised to the first power is equal to the argument, and we know that b to the first power is indeed b. Okay. Number 2, if we have log base b of 1 is equal to 0, because 0 is the exponent to which b must be raised to obtain a 1. And of course, we again see that here. B raised to 0th power is equal to 1. And so example 4, let's start with A real quick. All right, just to kind of show here. We would say, we would write 7, okay, 7 raised to what power is equal to 7? Okay, so we don't know the power is equal to 7. Well, obviously, 7 raised to the first power is 7, and we see that here. Okay. Next up, we have log 5 of 1. Well, we would say 5 raised to, again, what power is equal to 1? Well, there's only one power that will give you that, and that is a 0. And of course, we see that here. Okay. So those are two, again, they call them basic logarithmic properties because, well, they're pretty basic. We're talking about ones and zeros here. Alrighty, so next up we're going to talk about the inverse properties, and I think we can actually, well, we'll give them its own page. Okay, so the inverse properties are, kind of in the same realm of what we just did in terms of, it does make sense. You're just basically saying the same thing. So if I were to, and let's again start with, well, let's start with the definitions first. Sorry about that. So if we have b greater than 0 and b is not equal to 1, then we know that log base b of b raised to x power is equal to x. And we know that b raised to the log base b of x is equal to x. All right, so how do we get these? All right, well, again, we just going back to the very first page here. Second page. Of just basically going from logarithmic to exponential, and from exponential to logarithmic. So let's look at A real fast without even using the inverse properties. We're not even going to use the inverse properties right now. Okay, so for A, we would write this exponentially as 4, because it's a base, right? 4 raised to what power? Well, I don't know because we don't have an equal sign there. Is equal to, well, that's not equal sign. Is equal to, some number. We don't know. All right, and I'm not putting an x because, I don't know, it's just whatever. All right, so 4 raised to the what power is going to be equal to my argument, which is 4 raised to the 5th power. Well, that's easy. What 4 raised to what power is equal to 4 to the 5th? Well, that's just going to be a 5, and of course we see that here. Okay, and then for B, right, we have an exponential, right, and if we just follow along with our inverse properties of logarithms, right, and again, b raised to the log base b of x is equal to x, well, we have 6 raised to the log base 6 of 9. Well, that's just going to be equal to my argument, which is indeed 9. Okay, so those are some basic properties of logarithms, and I mean, you will be asked about them, but for the most part, your test questions are going to be, more in line with the harder stuff. All right, so the graphs of logarithmic. We're actually moving along quite nicely here. All right, so again, more snipping, I guess. I didn't intend for this, but that's the way it is. All right, so what this is wanting to know is we're just gonna look at the behavior of the graph, and this is definitely something that I don't want to graph because we really need to see the behavior. Okay, so if we have 2 raised to the x power, we learned in the previous section 4.1, we learned in 4.1 exponential functions that we shoot straight up, right, if our number is greater than 1. And of course 2 is indeed greater than 1, so we shoot straight up. We also know that we crossed that point 0, 1, right? We called that the landmark. That was the point that we shifted around. Okay, so that is 2 raised to the x power. Okay, well, log base 2 of x, okay, we don't know yet, but we do know, right? Um, so we have we crossed the point at 1, 0, and I don't know if we actually discussed why. Let me just go back. I don't, not necessarily. Okay. Well, if we plugged in an x, I'm sorry, if we plugged in a 1 for um, our x value here, then we know that log base 2 of x is equal to 0, right? Because 2 raised to the 0th power is equal to 1. And so we cross that point at 1. Okay. So in the red, you see the graph of the log base 2 of x. Now, again, I said that we don't know, but we do know, right? So what do we know about graphs that reflect across this line right here? Okay. Well, we know that they are inverse functions of one another. So here we are, example 6 into this section, and we just found out, even though you probably knew, we just found out that exponential functions and logarithmic functions are inverses of one another. That's very important to know. Very very important to understand. Okay, so these are the characteristics of logarithmic functions. Um, I think we can go on this page here. Yeah. Alrighty. So the domain again. Let's look at this. Okay. According to this graph, it looks like the domain is the numbers from 0 to 1, right? Like this graph exists all on the right side of the y-axis. So indeed, the domain is 0 to 1. I'm sorry, 0 to infinity. The range looks like, well, it goes all the way down. It looks like it shoots all the way down. And this, it's going up, it's going up, it's going up super duper, duper duper, duper duper, duper duper slowly, right? But it does go up eventually to infinity, okay? And it's very interesting. This is when I was an undergrad. Let me do something real fast. All right, so 65 million years in seconds. Let's see. Alrighty, so 65 million years ago, when the dinosaurs became extinct, was 2.05 times 10 to the 15th power seconds ago. Right? That's a very long time. So let's go ahead and just for it, because my undergrad professor told me this, and I thought it was kind of cool, right? So 2.5, so let's go 2.5, so we'll do O, and then times a to the 15th power. So we're going to go 1, 2, 3, 4, 5. So we got 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And so that is comma there, comma there, comma there, comma there, comma there. So what is that? That's million, billion. I think quintillion goes after trillion. Okay, so dinosaurs became extinct that many seconds ago. Now, interestingly, if you put this in your calculator, all right, so what is the log of this particular number? Where's my log button at? Here we go. Of 2, 0, 5, 0. Oh, 0, 0, 0, 0, 0, 0. Oh no, I might have missed. Ah, shoot. Hang on. All right. If I did the natural log of that number, all right, again, that number is in the quintillions. And again, I think quintillions after trillion. I don't know. But if I took the log of that number, then my value is just 35. All right, the log of that number in red is 35. So when I said, and again, this is like 10 minutes ago when I said this, but when I said that this goes up very, 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 very slowly, I mean very, very slowly. If I shifted, or if I found this number on the x-axis way down here, we would only be at 35 on the y-axis. Okay. Sorry for that little detour. I just think I think it's interesting. My professor made it interesting, and hopefully you find it interesting. So that is the that's how the range works, right? It goes all the way up to infinity. Well, that was just 0.1. Holy cow, Sherman, good job. All right, so the graphs of all logarithmic functions pass to the point 1, 0, right? It's pretty cool. Pass to the point 1, 0, which again, conveniently, is the mirror of 0, 1. What else? All right, so that's the x-intercept. There are no y-intercepts, right? We don't cross the y-axis. All right, if we have some b is greater than 1, then we have f of x equal to log base b of x has a graph that goes up and to the right. And if we are between 0 and 1, we go down and to the right. It's a decreasing function. Okay, and again, that's just going to be, and let's actually, so we know that if we had a decreasing function, a decreasing exponential function looks something like that, right? If we have the base between 0 and 1. Well, again, conveniently, the opposite would be the case for logarithmic functions. We would go down here and we'd go this way. Okay, and again, you can tell that's not a bad drawing, right? You can tell that these two lines are indeed reflective about this line right here. Okay. The graph of f of x, looking at number 5 here, equals log base b of x, approaches but does not touch the y-axis. Again, we kind of talked about that a second ago. And the y-axis, or x equals 0, is a vertical asymptote. Okay. Transformations, the transformations of logarithmic functions behave exactly like you think they would. The exact same way that we did with our parent functions, the exact same way that we did with our exponential functions. Okay. All right, so finding the domain of a logarithmic function. So how do we find the domain of a logarithmic function? New page. Okay. All right, so there are two ways to go about doing this. One would be, obviously algebraic. Second one would kind of be more in line with, what do you think? How about that? What do you think? Okay. So first of all, let's do it algebraically. Okay. So algebraically, let's go all the way back to the beginning here. Okay. So looking at this definition, for x greater than 0 and b greater than 0, where b is not equal to 1, y is equal to log base b of x. Okay, so we're looking strictly at the logarithmic equation. So y is equal to log base b of x. So again, x, notice it has to be greater than 0. X, again, like I've told you before, is the argument. Okay, so the argument must be greater than 0. So with that in mind, if we solve this algebraically, we would set that argument, again, the argument here is x plus 3, we would set the argument x plus 3, it must be greater than 0. Okay, and then of course if we solve this, we'd end up with x is greater than negative 3, and that's the domain. Okay, now that was pretty easy to do algebraically, but I also said there's another way to do it, and it's kind of, graphically, but graphically in your head, right? I've told you before, at this point, we really should get to the point where we can kind of graph these in our head, right? Well, we know for this particular problem, looking at the problem, we are adding to the variable. Okay, so since we are adding to the variable, that means we're going to make a horizontal shift to the left. Okay, and again, this is just the transformations that we've discussed ad nauseum at this point. All right, so if I'm taking this graph, and let's go ahead and kind of demonstrate here. Okay, so if I'm taking this graph that looks something like this, okay, and again, this is right here is going to be my landmark that I move around, my point 1, 0. Well, okay, if I take that line and I shift it to the left 3 units, right? This is 1, this is 2, this is 3. If we shifted it to the left 3 units, we are basically now at 2. Well, we can do better than that. We are crossing the point right here. This is the point -2, 0. Okay, because we shifted left 3 units, right? And since we're starting at 1, 1 minus 3 is -2. Okay, well, if we're shifting left 3 units, then our graph now looks like the green graph there. And if this is the line at -2, then this vertical asymptote here is at -3, right? Because again, the vertical asymptote is 1 unit to the left of my landmark, right? So all that to say this: since we're adding 3 to the variable, we shift left 3 units. We know that originally the vertical asymptote, or the domain, of our logarithmic function is from 0 to infinity. So we're just going to shift that to left 3 units. So instead of being from 0 to infinity, we're going to say from -3 to infinity. And of course, that's what we did right here algebraically. Now, I will say this. Doing it algebraically was quicker here in this particular case, but that's because I really wanted to explain the transformation that you can just basically do in your head, and you don't have to do the algebra behind it. You can just be like, oh, okay, so the vertical asymptote is normally at 0. We're normally from 0 to infinity. We shift left 3 units. So now we're going from -3 to infinity, and that's the domain. Okay. All right, next up we're going to talk about common logarithms. All right, so common log, I don't want to say, I mean, it's not, okay, without saying too much, we have discussed logarithmic equations. So log base b of x, okay? In this particular case, it is a base of b. If you just see log by itself, then it is an implied base 10. Okay, let's move this over to the left a little bit. It's an implied base 10. Now, if you see a log base e, okay, well, first of all, you'll never see, I mean, you might see that. I don't know, it might be try to be tricky. But if you see a log of a base e, then that is the natural log. And it's just written as ln. Now, it's written as ln. I remember when I was in school, and I mean, I don't do it anymore. Yeah, when I was in college, I would always read that as log natural, just because, I mean, it makes sense, right? It should be NL if it's natural log, but it's actually because it's Latin, like everything, right? Like everything, and it's actually logarithmic naturalis, so natural log. But anyways, so that is the logarithm with the base e, okay? And it gets its very own notation of ln because it is a very important number, and we'll see more of it. I don't know if we'll see too much of it in this particular course, but you'll definitely see a lot of it. Well, if you go into mathematics, the most I recall ever using it is in a course called Differential Equations, which is after Calculus 3. But anyways, all right. So in this particular problem, it reads: the percentage of adult height attained by a boy who is X years old can be modeled by our function here. Okay, so this reads. Where x represents the boy's age, so x is going to be the age from 5 to 15. Okay, that's more or less our domain, right, from 5 to 15. And f of x represents the percentage of his adult height. So approximately what percentage of his adult height has the boy attained at 8? So when he's 8 years old, what about how tall do you think he'll be? Okay, well, if he's 8 years old, and x is going to be how many years old the boy is, then all we have to do is plug in an x for this particular problem. So we would say, let's go ahead and rewrite the function. F of x is equal to 29 plus 48.8 log of, and then we're going to substitute in an 8 here, right? 8, and then plus 1. So it's basically, natural log of 9, right? And if we put all this into the calculator, we end up with approximately, okay, so approximately is the equal signs of squiggles, right? And those aren't, I mean, they're okay squiggles, but instead of writing straight, because that means that they are equal to, like that is an equal amount. But since this number is not an equal number, we do little squiggles. Then they're called tildes, Tilde, tilde, maybe tilde, I don't know. Right? And that's going to be equal to about 76. So an 8-year-old boy has attained approximately 76% of his adult height, right? So approximately 3/4 of his adult height. And well, that's it. That's simple plug and chug, right? I'm pretty sure. No, sorry, I'm just getting ahead of myself here. Yeah. Okay. Let's look at properties of common logarithms here. So the properties of common logarithms are going to be about the same as our general properties. Okay. So if we see here, we had our general properties that we did earlier. Well, the common log, I don't think okay. So on this particular page here, right, this is also known as the common log. I should have written that, I'm sorry. Common log, okay? You know what? No. Common log, right? So if we have a logarithm with a base of 10, it is referred to as the common log, and as I mentioned, you don't have to write the 10. Okay, the 10 is kind of redundant. It's kind of like no, oh no, shoot, the 10's just going off everywhere. It's 10. Okay, it's kind of like writing the square root of x. Okay, we know that whenever we see this radical, we know it's a square root, right? We know it's a square root, even though there's not a 2 there. We know it's a square root, right? As opposed to something like a cube root, where we do have to write the 3, right? If we didn't write the 3 there, then you would think, oh, well, that's the square root of x. Okay, so that's the idea behind common log. Common log is just the logarithm with a base of 10, and that's it. That's really it. It's just a logarithm with a base of 10. We just don't write the 10 there. Okay, and the properties are all the same. Okay, this is another plug and chug problem, um, but I guess we'll go ahead and we'll just do it like this. Alrighty, so the magnitude R, okay, so R is the magnitude on the Richter scale of an earthquake of intensity I. So we know magnitude is R, intensity is I, is given by, I'm sorry, excuse me, is given by R is equal to log of I over I sub 0. Okay, so now I sub 0 is I naught, which is initial intensity. Sorry, I've got the burp hiccups. I hope it doesn't pick up too much on the microphone. I'm sorry. All right, so where I naught is the intensity of a barely felt 0 level earthquake. Okay, so we're told what R is, we're told what I is, and we're told what I naught is. The earthquake that destroyed San Francisco in 1906 was a 10.83 times as intense as a 0 level earthquake. What was the magnitude on the Richter scale? Okay, so the way we solve this, right, is we're just going to say, okay, so we have our equations. Let's rewrite our equation real fast. Well, that didn't really do anything, did it? Trying to italicize my I there. Okay, so that is my equation. Right, now we're trying to find the magnitude. Right, the magnitude is R. So what we're going to have to do here is we're going to have to substitute in a 10.83 for 10.83 times as intense as a zero level earthquake. So if a zero level earthquake is I naught, okay, then what is 8.3 times I naught? Well, it's literally just 8.3 times I naught, right? So what we're going to do here is we're going to replace the I in the numerator with a 10.83, I'm sorry, 10, did I say 0.83 earlier? I'm sorry, 10 raised to 8.3 power of I naught over I naught. Okay, and again, all I did was the intensity of the earthquake. Okay, we cannot write just simply 10.83. Okay, because I mean there's little context there. 10.83 what? Well, 10.83 times a barely felt earthquake, which is nothing, right? So it's important to do that because computationally, that way my I naughts will cancel, and so I basically just end up with a log of 10 raised to the 8.3 power. So we end up with a log. Man, I'm struggling. I'm unwinding fast here. Log of 10 raised to the 8.3 power. Now the thing is, we don't have to necessarily write that, or we don't have to necessarily have to compute that, right? Because we know that this is an implied base 10, right? And so if we were to write this entire problem here, you know, basically as an exponential problem, we would say 10 raised to the, equals to, we don't know. Is it 10 raised to the what power is equal to my argument, which is 10 raised to the 8.3. Okay, well, I mean, hopefully it's obvious. It's just x equal to 8.3. So this particular problem, the solution is just simply 8.3. Right? R is equal to 8.3. We have an 8.3 magnitude earthquake. All right. Natural logs we spoke about. Okay. So the last thing we're going to do is we're going to talk about, let's actually bring about the properties of natural logs here first. Okay. And we'll just go ahead and throw in this domain problem. Okay, so looking at the properties of natural logarithms, like I mentioned before, natural logarithms are just logs with a base of e. Okay, just instead of saying log base 2 or log base 3, this is log base 2.71828, all right, or e. And again, the properties are the exact same here. Okay, so how do we find the domain of each function? Well, I mean, finding the domain of a pretty simple. It's exactly how we did the finding the domain of that problem, right? We just basically, we could do one of two things. We could either solve it algebraically, or we could just kind of do it in our head. Okay, and so by doing either of those cases, we can see that we have the domain is from negative infinity to positive 3. Okay. Now B is a little bit different, and there is another algebraic way to do it, but since the book isn't really talking about it, I don't necessarily find it imperative that I do as well. Instead, what the book does is it graphs that natural log, and let me see if it actually shows the graph in here. Yeah, here it is. 4.5. Yeah. Actually, heck, we'll just pop both these in. Didn't even think about that. Okay. There we go. Okay, so looking at the graph of B, again, doing this graphically, you will be able to see that we do indeed have the domain from negative infinity to 3 union with 3 to infinity. We see that we have a vertical asymptote right here at a positive 3. Now again, there is an algebraic way to do it, and I I'm pretty sure we do. I guess we just do it in pre-calculus. If we do circle around to it in this course, obviously we'll get there. But I think the book is kind of harping on using a calculator, which I hate, but it is what it is. But anyways, that does conclude today's lecture.